So our next talk will be from Azita Valinia discussing the NASA Engineering and Safety Center update. Take it away.
Thank you, Kelsey. A quick comm check.
Loud and clear, thanks.
Very good. And thank you to the organizers for inviting me to give you this update on NASA Engineering and Safety Center, or NESC. For those of you who may not have heard about us, NESC was established in 2003 after the Columbia accident to provide an independent technical resource for resolution of challenging problems for NASA programs and projects. And about 70% of the work that we do at NESC is in support of HUOMD and 30% in support of Science Mission Directorate. Next chart, please. So I've put here a list of projects that are currently under works at NESC. There are about 60 recent or ongoing projects, and this list hopefully will give you a flavor of the topics that we are tackling at NESC. Most of them are focused on hardcore engineering analysis, study, and tests in support of Artemis. But there are some here that I thought might be of interest to this group. There is a lot of work on space radiation and environment, space weather architecture options for human NASA missions beyond low Earth orbit, Moon and Mars. This audience probably is familiar with the Lunar dust workshop that NESC ran last year, studying the lunar dust impact on human health and operations. And also there are a number of assessments going on in support of environmental control and life support systems, or ECLSS. For the rest of this talk, I'd like to talk to you about a current study that we are doing at NESC on safe human expeditions beyond low Earth orbit. And as I think you all agree, especially given the last talk by Steve, science return during human expeditions is highly dependent on human health and adequately integrated human systems architecture. So our study is focused on minimizing human health risks and also better integrating human systems architecture. Next chart, please. So before I tell you more about the elements of the study, just want to remind you very quickly a recent Physics Today article by Larry Townsend last year gave some statistics that are quite enlightening. Apollo astronauts spent a total time of only 80 hours outside the lunar module and less than 3 months in space travel over a period of 4 years. So although in the last 20 years we have gained a lot of experience with human expeditions on ISS, our knowledge and experience beyond LEO with human expeditions is quite in its infancy. And so we are now talking about going to the moon in a sustainable way and staying there for several months, and to Mars on the order of several years. So some of the hazards that we are focusing on our study obviously are space weather events and galactic cosmic rays when astronauts are outside of the Earth's protective magnetosphere, and also long duration flights with variable gravity and delayed communication with Earth pose additional risk. And this is actually more relevant to the Mars mission, but could also be potentially risky for lunar missions as well. Next chart, please. Okay, so I've tried to put the elements of our study, the focus, into one chart. We are primarily focusing on engineering solutions to minimize health risks on long expeditions beyond LEO. For this study, we are focusing on specifically 2 design reference missions, or DRM, the lunar mission of at least a month to a year, and the Mars mission, which will be on the order of at least a couple of years or more. On the left-hand box here, I'm showing you the expedition focus for these two DRMs. Mainly characterized by extreme space environments, and number two, by long duration, which is characterized by variable gravity and delayed communication with Earth. So thanks to Steve, who just, through the RIDGE acronym, explained the 5 primary areas that they have narrowed down in the HRP program on human health. We are focusing in the middle column here only on 3 of those human health hazards: radiation, distance from Earth, and altered gravity. And on the right-hand side column, I'm showing the technology and engineering focus of our study, which is radiation mitigation, human factors, autonomy, and creation of artificial gravity. Next chart, please. Okay, so this is an eye chart, but there's a reason I'm showing you this. This is a summary of NASA human systems risk. And on the left-hand column, there are the 5 major hazards with risks under each of those hazards. They add up to 30 risks. And on the right 2-hand columns, I'm showing you the 2 DRMs that I talked about, the Lunar and the Mars mission. And you can see the risks, the classification and the risk ratings are approved at the Human System Risk Board at NASA. And what I want to show you and highlight is that these risks are mostly yellow or red for both of those DRMs, and they require mitigation. So our study here is quite complementary to what HRP is doing. HRP has a robust research program, as Steve mentioned, and they're working on countermeasures for each of these risks, plus a lot more. What we are doing, we're looking at the whole holistic human system, and by coming up with a few engineering solutions, we're hoping to be able to knock down or mitigate a lot of those risks at the same time. Next chart, please. So just to summarize some of the elements of our interdisciplinary study on the left-hand side, we have a space environment and shielding core group led by Joe Mino. What they're doing is calculating radiation environment and comparing them in LEO, Lunar, and Mars design reference missions. They're doing shielding trait studies using vehicle models and transport codes. They're studying the impact of solar particle events on operations, including extravehicular activities, and also looking at a number of other things, such as looking at the next generation of space environment architecture. In the second column, you may or may not have seen in the previous chart when I showed the risks, there is a red risk for both the Lunar and the Mars mission called inadequate human systems integration. And our study is focusing on that, trying to nudge those toward yellow. And what I mean by that are, as an example, rethinking the design and onboard operational supports when some events, for example, space weather events, impact the spacecraft, requiring the crew to intervene without much assistance from Earth. So the end result is to develop standards for crew carrying vehicles on long journeys to support this increasingly Earth independent crew operation with increased reliance again on automation, robotics, and intelligent technologies. And then the final pillar of our study focuses on Mars fast transit trades. I won't go much into that other than saying that we're doing a lot of trades using nuclear thermal propulsion for the radiation exposure difference between nominal transit and fast transit. So all of this study is ongoing right now, but it will culminate in a NASA public workshop in September to gather community's input and integrate the findings. And next chart, which is my last chart, I just want to give you the dates and hope you save the dates and join us in September of this year. We are hopeful and optimistic to be meeting in person in Houston. The URL down there has information about the workshop, and if you look us up, you can get on our distribution list, and we'll send you updates about the workshop. And thank you. That's all I have.
Thanks so much. It was great.